c'est bon, on peut pas obligé de simplement aller dans la...
Non mais tu dis que tu as dit qu'il fallait... C'est pour ça que j'ai besoin de on rentre pas beaucoup dans le détail. Je raconte, on n'a pas fait de déterministique aussi, on a le déterministique, là, on n'a jamais fait de déterministique. Je peux parler déterministique. Je suis prêt. Est-ce que je me sers directement de mon PC pour te présenter? Alors il faut que je sur le microphone. Ok. Je vais écraser directement les slides non contenantes. Ouais. Bon. Je me contente de cacher les slides archives. Et deux. Bon, je vais faire de toute façon pour vous. Ah. Ok. Bon, ben. Ah, c'est toi qui veux. Ah, tu veux présenter. Bon, vous présentez avec le côté. Ouais, je prendrai fil plus tard alors, le DGA. D'accord. Okay. So we leave a second for people to sit down and we'll start the meeting. Are the blue sheets circulating? Can you please circulate the blue sheets? So, do we have a Jabber note taker? Diego, are you taking the Jabber note? Are you on Jabber? And the minutes taker, Dominique? And Nicolas, fantastic. We'll be sharing this meeting on the Etherpad, as usual. Okay. So this is the link to the Etherpad that we use for 6TISCH. So that's useful for people remote because if they don't understand what's going on in the room, they can still read from the Etherpad. So the minute takers will be using the Etherpad, but you're free to actually use it as well to add some stuff in there. So this is an IETF meeting, so we proceed with the classical not well. In particular, you'll note the best practice for IPR. Your presence is being logged. The meeting will be recorded. There will be a remote attendance to this meeting as well as local attendance, obviously. And we'll publish the minutes and the proceedings to the IETF site. So we had in plan to have 2 6TISCH sessions for this meeting. One which would be directed towards new work that might happen at 6TISCH or be related to 6TISCH, and then the core of the 6TISCH work. Now we just have had a talk with the area director who basically told us that work which would be too far from the charter would not be appropriate for this working group. So we'll have to skip the first 3 documents that we expected to discuss on .NET today. and we'll be instead presenting some work that we'll be presenting again at PCE on Wednesday, which relates to basically the applicability of PCE to 6TISCH. So from the agenda as we meant it, the first 3 items, the first 40 minutes are skipped and will be replaced by a discussion on .NET and more particularly PC applicability to deterministic 6TISCH. And so we kept the slides there for...
Can I just ask a question?
Yeah.
So what's the plan for those first 3? Where are they going to go?
They won't be discussed here, but what we'd like to do is make a bar off outside this room. We can't stay in the room even if we... I asked Ted, right? If we stop earlier, can we keep the room to have this discussion? Ted said no.
Okay.
You don't? Okay. So we'll start with this discussion about PCE applicability to 6TISCH, and then we'll go straight to draft 1 6TISCH track use case. And then we'll have the security discussion. Michael is telling us that there is nothing new to discuss about the design team, so we'll go straight to draft strict 6TISCH security considerations. So we expect that we can talk a lot about security today.
Actually, let me restate. I would like to spend time talking about the security parts of the chartering, the chartering.
Yes, and that's part of the wrap-up. So we'll have a long wrap-up as long as we like, probably. And with this, I'll be skipping a number of slides. So we kept the slides in so that you have the slide number on the PDF, but we won't discuss the slides, so I'm just going to skip. So one potential goal is to try to get a work group forming BOF in Prague, where the slides will be presented. And with this, I will move to this. On commence par les liens.
Just 1 second.
Oh, no, okay, Lina.
Hi, hello everyone. This is Zhuo Chen. Here today I'm going to present some use case and requirements for using track in 6TISCH networks. So this is a new draft. It's just uploaded before this for this IETF meeting, and and actually it's available on the working group webpage. So there are many use cases in low power and lossy networks. For example, there are industry networks, there are home networks, building networks, and healthy networks. Today I'm going to focus on the industry network, and because this is the most attractive use cases for the track in 6TISCH networks. So this figure is the same as in the 6TISCH architecture document. So in a 6TISCH network, there will be a central controller or gateway in the network, and there will also many LLN devices in the network. And there will be also a PCE in the network to do the path computation. And today I'm going to present like 2 applications. The first application is industry process control and automation applications. For example, automation assembly line. So in this application, the LLN device 1 may be an actuator in the first step of the automation assembly line. And the LLN2 may be another actuator, which is for the step 2 of the automation assembly line. And the LLN device 1 will periodically send the package to the LLN device 2. For example, if the LLN device 1 just finish a task, it needs to send a signaling packet to LLN device 2 to trigger the next step action. All this packet is really delay sensitive because the delay determines the performance of the assembly line. And also the reliability of this packet is really important because a packet loss may result a defect product. Therefore, a track needs to be reserved from the LLN device 1 to LLN device 2 to solve the problem I just mentioned. So the second category of applications is we call the industry monitoring applications. For example, the LLN device 1 may be a sensor. It may send some critical event and send the signaling message to the central controller. And after it sends the signaling packet, it may follow with a bunch of data packets for the monitoring data. For the signaling packet, the delay should be minimized, and also the reliability of this signaling packet should be extremely important. Therefore, there should be a track reserved between the LLN device 1 and the central controller. And there is one more requirement for this type of track is because LLN device 1 will send a burst of traffic. Therefore, there should be some track reservation scheme that can be dynamically changed to reserve resource. So here summarize some benefit of using tracks. As I mentioned for the previous use cases, a track can guarantee the low loss and less overhead in the network. And also, an important thing is for the constrained networks. So reserving a track can enable the sleeping node and also save the energy of the node because every node knows its schedule. And also because the track is scheduled, there will be less interference in the network, so there will be the reliability will become better. And as discussed in the architecture, 6TISCH architecture draft, there are two track reservation schemes. One is called the remote track reservation, and another is called the hop-by-hop track reservations, but it's not so many detailed information in the architecture document yet. Here is some requirement for a good track reservation schemes for the 6TISCH network. First kind of track reservation scheme is we name it called centralized track reservation scheme. And for this centralized track reservation scheme, so there are two requirements. The first requirement is the central controller, for example, or the PCE in the network. It needs to know the topology and all schedule information of the network such that they can schedule the resource and reserve the track. The second thing is after the central controller want to reserve track, it require a protocol for the PCE to communicate with the LLN devices in the network. And this protocol should be extremely lightweight because all the LLN devices in the network are constrained devices. It cannot support heavyweight protocol like TCP, for example. The other category of the track reservation we call distributed track reservation. Because the LLN device 6TISCH network may become a big network, in that way there may be some case the centralized scheme may become a bottleneck of the network. So it may also require a distributed track reservation scheme. For the distributed track reservation scheme, actually we need a fast reaction protocol. And we also need a protocol to quickly deter a track failure. So we can start another process to reserve another track. And we also need to a negotiation protocol between the LN device if they are multi-hop away from each other. And this is the next step is like we want to probably discuss in future about like how we can have like this kind of like track reservation schemes in the 6TISCH networks.
Thank you, Chonggang. Do we have questions in the room for this draft?
So, Thomas Watijn, I have a question. Did you mention anything about redundancy? Have you thought about the redundancy? Because if you reserve a single track with a sequence of wireless nodes and one of these links fails, then your track and all the reliability you get from it disappears. What are your thoughts on this?
Yeah, for example, like I mentioned, you mean the kind of track maintenance, right?
Sure.
So there will be detected a failure, and then probably there can be several schemes like for the centralized scheme, the PCE can know that by some way, and it can kind of like reserve another track. Okay. And this is quite interesting problem. Probably we can also, like, this is kind of solution of this.
What I'd like to understand is the relationship between the track reservation and things like the 6-stop interface, the JSON 6-stop interface, and what we need to, the Yang 6-stop interface, and what we need to change to make space for this and to allow for. Oh, hello. The relationship between what you're proposing with track management and the.
All right, this is Thomas again. So what I would encourage, since you're asking for next steps, what I would encourage is to look at the relationship between what you're proposing with track management and the Yang-based 6-stop interface document and see what we have to change there, because we're almost ready to conclude that work and say that this work is done. And this is very, very important work, and we have to absolutely make sure that we have track management. And so what I would ask you to do as a next step is to look at the impact on the Yang-based model of this work.
Actually, I already looked at the interface model. I think it's not contradict with the interface, because in the interface we have a lot of command which also deal with the track, right? Yeah. Like the track create, delete, this kind of command.
So exactly to your point, I'm not saying that this is a contradiction at all. Okay. This is exactly within scope. Yeah. I'm just asking, do you recommend some changes to that model based on what you just presented? And if you do, please let us know, because we have to.
Yeah. The last call for the.
Exactly. Thank you.
So how are we going to do this?
You can come.
Came back?
Kong, please come here and use this mic.
This is Chong Gang, the co-author of this draft. I like the question Thomas just mentioned, what's the relationship between the redundancy consideration and also the current 6-stop interface. because as I know, and I also reviewed the draft, it's quite complete.
Excuse me, can you please hold your mic like this? No, like
This
this.
way?
Yes.
Okay.
Yes.
But the purpose here, the use case here is mainly try to see based on the current 6TISCH architecture and the 6-top interface, we found out that there is some in terms of requirements we try to consider. But in terms of solution or something else, that's the next step. But here we just bring these requirements to the working group, see if we can have agreement about these requirements. And after that, we may take the current 6TISCH draft architecture, 6-top co-op interface, take them as the existing document and see where we can go. Yeah, that's the main goal. Thanks.
Thank you. Pat Kinney Consulting. Can you go back to the picture? Oops. That one. Thank you. By the way, TSCH is a operation that's done in the industry right now, wireless HART, but also ISA 100.11a, and you'll see that often. As far as the redundancy, to address Thomas's point, which is a really good point, 11a has a feature, they call it dual cast, where if you look at, let's say, LLN device 1, there could be one device talking to, and within, let's say, listening distance of a couple backbone routers. Dualcast allows then that if one backbone router misses it, it'll still go through, so you won't have to repeat the message. So it is actually a very well used capability in 11a that I think we should look into.
Okay. I can only agree. I mean, I would basically extend this point to asking Chonggang to consider the DetNet architecture, which will not be presenting today, but the DetNet architecture presents the concept of frame replication and elimination, which is a generalization of dualcast. Mm-hmm. And the operation by a node may be forking a packet, that means making two copies. In your case, it's just promiscuously listening, right? Dualcast is a promiscuous listening by two APs or two backbone routers. But in the general case, there may be a node in the network which is capable of making two copies across two different paths, and another node in the network which is capable of recognizing two copies and sending only one, which is the generic question of frame replication and elimination. And now Thomas' question to you, Chonggang, becomes, can we first document this operation in your draft, and second, look at the 6-top interface document, whether we can actually program this operation into the device, because that's clearly a need from what I hear here.
I would mention before Thomas speaks, because he wants to speak right now, for dualcast to work, we found in the industrial area that the time slot needs to be slightly wider. So instead of, excuse me, like 10 milliseconds, make it almost 12. But we have that capability already in the 802.15.4, so there's no issue there. It's just, it will work better when you do that.
Yeah, so you got my question before I asked that.
Oh, sorry.
No. I mean, you answered it. It's great. The dualcast, is it something that works with 15.4e as today?
Yes.
Perfect. I
Absolutely.
want to make sure that this is the case that we.
And it's 15.4 now, by the way. It's not anymore.
15.4 2015.
Okay.
Well noted. Thank you.
Quick question there. I thought that dualcast has two ACKs.
Adds
two acknowledgements, one per
yes.
router.
Yeah,
so
that's why you want a little bit wider time slot to allow for multiple acts.
Right.
But it is possible.
Okay. I haven't seen in the published 15.4e 2012 that I've seen. I haven't seen the case where there's two acts. Is this something we can play? I mean,
yeah. Let's talk about that.
Okay.
Okay.
Thank you.
Thank you, Ben. Thanks a lot.
I was going to give this back.
So I take it that this frame replication and elimination model that exists in DetNet is of use for 6TISCH as well. That's my conclusion for this discussion. And, we'll have to plug this on the laptop.
Oh, I thought you said X.
Yeah, that's what it says.
On va faire mon truc. Ok. Okay, so this is a presentation that I actually prepared. Oh, it's not the right one. Excuse me. Yes, this is. Okay, so this is a presentation that I prepared on a request from the PC working group to basically explain what 6TISCH is doing, what deterministic networking is doing, and how that could be applied to PC, how PC could actually help in that process. Oops. Is there a way to move the projector a little bit? Well, so basically what is deterministic networking? It's mostly non-precedented level of guarantees from an IP network. It's something that has been around for 40 years in industrial networks for factory automation and process control application, but it's not something that has drawn interest in the IP world. So for us, it's a new frontier. Today, it's already used as a differentiator for high-end forwarding engine like AVB switches, audio-video professional audio, this type of switches. It's also a differentiator for high-end modes, whether it's wireless HART, ISA100.11a. Those are actually high-end devices which can provide levels of guarantees that are unprecedented in the radio industry. And an additional requirement that we just got from Chonggang is that a network has not only to be able to provide this new level of guarantees, but at the same time still serve classical best effort stochastic IP packets, typically the REPL packets that we serve with minimal 6TISCH. If you want to provide any sort of deterministic guarantees on your traffic, in the first place, the flow that are incoming your network must be deterministic. A classical type of deterministic flow is an industrial control loop whereby a sensor sends periodically at a very precise period a sensor reading that goes to a programmable logic controller, which is some kind of logic device which is close by the sensor. Then the PLC, this programmable logic controller, makes some decision about some actuation, for instance, heating the ketchup or something. And that goes again across a deterministic path so as to arrive to the actuator at the precise time. And this goes over and over and over. In process control application, this is very slow. This is a few times per second. In factory automation, where they produce individual goods, like cars and parts or whatever, this can go at speed to hundreds of times per second. And when it's motion control application, it can be thousands of times per second. And, well, the only way we know of so as to actually guarantee that the packet will arrive exactly at the right time, if it comes in exactly at the right time, is by synchronizing the network and providing global schedule of how the network works. Well, at least a global schedules at the egress point, which is what ProA does today. But what we are considering for 6TISCH is a tight synchronization of every device and a schedule that applies to every device. So to explain better what deterministic is, I have two simple analogies. One is the train analogy. And the train analogy says that basically what we want to avoid with trains is collisions of trains on the railway. That could be a bad idea. And to avoid this problem, we guarantee that a railway track, will be used by a single train at a single point of time. And to do that, what we have to do is, if there are several trains at the station, you have to put some trains on the side and schedule which train will leave the station. Which means that the train will arrive at the station at a certain time, will have to stay there, maybe be taken outside of the main way so that another train leaves. And then in due time, this particular train will leave from the station. And you program the whole railway system in your country, and now you've got a deterministic network of trains, and hopefully you don't have any train collision. That's how we avoid collision loss. You know exactly how many buffers, how many rails in parallel you've got in every station. That's how many trains you can store there. Then you compute how much time the train will stay in the station, and you schedule it for the next hop to the next station. The other analogy that I have for deterministic is the bus system. What?
Not in my city.
Okay. Sorry. So the expectation there is you've got a bus at a precise time, say every 15 minutes. And you know that from point A to point B, your bus will take like half an hour. So the worst time for you, once you arrive to the bus stop, is something between 0 and 15 minutes to see the bus coming, and then 30 minutes to get there. And what you're interested in there is this 45 minutes. You don't care about the 30 minutes. Only the worst case is of importance. You know that you'll be at work 45 minutes at worst after you arrive to the bus, the abri bus, the bus stop. Okay? So 45 minutes is your worst case scenario to get to work or to get back home. And with this, if you schedule a bus at the precise period you want, then you can reduce actually the worst case scenario to something which fits your needs. And if you look at an Airbus 380, that's exactly how everything works in a 380. A 380 is completely computed in advance. Every flow is a bus. For instance, when the pilot will move his joystick or whatever it is, there will be a bus every so many milliseconds to take the command, go through the whole Airbus switch system to reach the controller where the command is understood. Okay? And so you're guaranteed that if it's every 5 milliseconds, for instance, you're guaranteed that if it takes like 3 milliseconds to go through the switches, then at worst 5 plus 3 milliseconds, the command from the pilot will be taken into account by the controller. And that's a guarantee. But that also means that the hops that this particular command takes, whether the pilot does anything or not, these hops are reserved for this particular activity. In an Airbus, everything is reserved. You don't have best effort. Now, in a more classical, like a 6TISCH network, we expect to have both those tracks, as we call them, which we call those buses and which are there periodically for a deterministic path. And at the same time, we want to be able to reuse those time slots if there is nobody in the bus. Right? If the bus is not needed for this particular iteration, then we want to be able to reuse the time slots so as to not waste them. Okay, and who needs deterministic networking? The first example is the one that Chonggang has been giving us. So that's wireless HART, ISA, etc., all those industrial control loops. Now, we are not the only users, and that's why we are looking at DetNet. Another example of user is happening on 802.1. So initially there was the audio-video bridging work, which has delivered the first generation of devices, which basically can queue at the edge of the network and deliver the packet just in time. And now there is the new work at 802.1, which Norm here is leading, and which is generalizing the problem and taken into account different types of scheduling into the network. And the sort of problem that DetNet is addressing is exactly the sort of problem that we are looking at. How can we expose a topology to the network? How can we expose the device capabilities to the network? How can we express a path, a track? What sort of capabilities do we want from this track? All this is not specific to 6TISCH. A little point about determinism, it's back to physical. We do a lot of virtualized, over-virtualized. Here, we're talking about real buffers. We are talking about real queues. We are talking about real time. We need to know, think about your trains, right? You want to virtualize your train, the station. There are more trains than there are lines. You've got a problem. You need to know exactly how many trains. You need to know exactly how many ways. You need to know the exact departure time of your train. And that's how you can schedule anything. What it's not about is layers, protocols. You can schedule a layer 2 network. You can schedule a layer 3 network. This is not important. You can schedule an IEEE network. You can schedule an ISA network, an IETF network. This is also not important. What is important is the sort of operation that you expect from the network. Tight synchronization, scheduling capabilities, how many buffers do I have in my forwarding system. So with this, we started a DetNet effort, which is a generalization of what we initially foresaw at 6TISCH, but it's also an integration of what IEEE has been doing at 82.1. And we thought, okay, if the basic model for a 6TISCH track was like this, then we could basically say, okay, let's use some ripple TE. I don't know what that would be, but some ripple TE, which would probably be based on the reactive point-to-point ripple that is an experimental RFC, and draw an optimized path between a sender and a listener, and mark the hops, reserve time slot, do something along this path, and call it a track. But as we discussed earlier, and I have an example exactly of what Pat has been talking about. Well, I don't have a geocast really, or this could be seen as a geocast. But we've got an example here of frame replication and elimination. There is a single frame going outside the NIC, but it's actually forwarded here and here. So if this copy is lost, this copy will still fly. Not only this, if this copy is lost, not only this copy will still fly, but it will still arrive here and here. So if this one is lost now, this one can still make it. And why do we do those frame elimination and replication thing? It's because we want to guarantee the time of arrival. If you were doing ARQ retries, or HARQ, when you have got some FAQ in it, you would not be able to guarantee the delivery time because you have to wait for acknowledgements which don't come. You start doing retries in some max, exponential backoff, and now you don't know when your frame is going through. So if you want to guarantee the time of arrival of any of those two copies, then you need to basically schedule those two sending, and when those two receive have been done, then you can schedule those two sends. Okay? This means that this node recognizes that this copy and this copy are the same, and makes two copies of the same packet this way. That's the elimination and then the replication. And that's how one of the copies has a better chance to arrive in time. If you want to do that in the distributed fashion, well, nobody knows how to do it. We have not found it. And if you look at the way industrial people do, they all use a centralized controller to do this computation. So in wireless HART, it's called the manager. Is it? In ISA 100.11a, it's a system manager, right? And in WPA, I don't remember what it's called, but they still have one centralized entity, which basically will do the route computation, taking into account the level of reliability that you want, which means how many backup paths you have, and the latency that you can afford. If we look at this controller, now you wonder, okay, what do I feed into the controller to get my path realized? And what does the controller need to feed into the network? So the model that we are seeing here has some application, some user needs, which is in the SDN model above the service layer interface, which sometimes is called the northbound interface. And on that layer, you basically describe a need. I want to go from here to here with this level of reliability. My throughput looks like this. The data I'm pushing into the network looks like that. This is not exactly the piece we're interested in, but this needs to be specified. Now, based on those needs, one or multiple controllers may coordinate so as to actually install state in the network, so as to actually provide the forwarding capabilities that were requested. To get there, you need to install state in the network. You reserve this buffer at this time for this flow. You also need to tag the packets with the flow IDs so that you recognize in the intermediate node, oh, this is packet 5 from flow A. Here is when I receive it, here is when I send it. I need to duplicate it. I need to coalesce those two receive into one. Okay, so all this needs to be programmed in all the intermediate devices. So there is a need to first expose the topology that resides here into the controller. And this is the sort of work that I understand is being done at TISCH. And then there is a need to push down all those state, including time. And I understand that the sort of work which is done at CCamp, because this actually, if you look at it, does not depend even on IP. I receive something on this time slot, I send it on this other time slot. It's a GMPLS way of doing things. So that's why CCamp is something that we have to have in scope when we think about this model. Now, if we move more into the controller, we see that there is an alternate way of doing things. You know, T starts on one side and goes along. But here we've got those replication and things, so we would have to make it more complex. The alternate way from going from the source and going all the way is actually to program everything from the controller directly to the devices, which is not exactly the model that PC is doing. PC is a T thing, so it starts at one end and goes all the way to the other. What we could want to do, and we have to think about it, is using the PC protocols a bit differently so as to program the devices individually. So if I have computed all the flows which go to this device, as opposed to injecting all the flows one by one from the endpoint, I would basically coalesce for every device the schedule, the resulting schedule, and saying, oh, if you receive something there, just send it there, don't even look at it. This goes there. Okay, so that's an alternate model for actually implementing a deterministic 6-TISCH. Now, Norm, this is for you. I really need you to look at this one. If we expand the view of the controller, we have basically it's a network management entity. If you look at it, it's a very big, huge network management entity. Now, what do we find in this management entity? The first thing you find is something which echoes what you can do on a router with a CLI. Is how do I configure something new? How do I send a command? Shutdown, no shutdown. So this is basically the thing which populates something onto the devices. So that would be your northbound, that would be your southbound interface from a SDN infrastructure down to the network. What you also have for 6-TISCH is some entity, and that's the PC really for us. An entity that is capable of taking a topology, taking some requirements, and computing a new route, a new set of time slots in every device so as to actually implement the track that we are talking about. So the track computation, and then when there is a breakage, the track maintenance, we expect it from the PC, and that's really the positioning that we see and that I want to push to see how PC people react. And then there is a first element, which is really the operation of my network management. Measuring if I get the throughput I want, measuring if I get the latency that I want, measuring the packet loss, which are not unexpected, and then taking action to correct the faults. And in runtime, that's really the fault management that will drive the PC into maintenance to reprogram a path that will end up into new commands to actually remove the broken path and set up a new one. So that's why I've got the arrows in this direction. And that will be my conclusion. So 6-TISCH has a tight time synchronization. That's a deterministic MAC. So far, we have been doing the hard part, actually, which is how do I use a deterministic MAC for stochastic traffic. Now we want to use the deterministic MAC for what it's designed, which is deterministic traffic, and we can do it because we have this scheduling information, these scheduling capabilities. To be able to do that, we need to connect to PCE, CCAM, TISCH, and many others. And we have to identify exactly what goes where and what type of work has to be done. As we look at it, we realize that these operations are very similar, if not completely congruent, with the operations that are in the draft DetNet architecture. If that's so, then what we really want to do is implement the draft DetNet architecture and apply it to 6-TISCH, which would basically mean that 6-TISCH would put requirements into DetNet, and DetNet would share those requirements with other requirements and apply CCAMP, TISCH, PC, and others, I don't know, to actually provide the services that DetNet needs, and thus that 6-TISCH needs. And that's basically it. That's what I wanted to say. So we'll rediscuss this at the charter and how we work with DetNet, whether DetNet should be an entity by itself, etc. I hope we have a discussion on that at the end of this meeting, and I'm done. Question?
Any questions? Any questions?
So Pascal, do you expect that PCE is going to configure it once, and how often do you expect that the controller? And I'm thinking like you might be thinking about SDN controller having a PCE component in it.
Yes.
Okay.
Okay. So my vision is that. My vision is that the PC is actually an active component into an SDN controller. Right? So you can call it an SDN controller, you can call it a network management entity. I mean, ISA100.20 calls that CNM. And so whether the way you call this entity the overall controller is secondary to me. What I'm interested in is saying, okay, the PC must be able to understand needs such as frame elimination, replication, real-time, time slots, all those things. It must be able to compute from an abstraction of a topology, an abstraction of a schedule. And now it should push that to you remember my 3 square, right? The square on the left, which is the thing which talks to the network. So the way the PC talks to that thing, to that controlling, the CLI thing, is orthogonal, should be separated from the way this thing talks to the network. So it can talk open flow, it can talk open daylight, it can talk PSAP. It could be anything. What the PC talks to that thing could be a single way.
Yeah, the reason I'm asking if there is movement, and I wonder if the movement latency, if it might move at a speed, and you need to configure at same level of with the same level of latency. So do you expect, because these kind of elements, central controller and maybe network management system, they have a very high latency usually. So
okay, so if you look at deterministic networking architecture, you'll find that you have 3 core components. And one of them nails down a path. You can have a solution which does not do that. You can have a solution which basically does the frame replication elimination, but is stochastic inside the network, so as to enable more dynamic routing. In which case you have to push the latency control, the buffering of packets, so that you can ensure the latency at the edge of the network. Right. So the 3 elements is nailing down the path, reserving something. You've got the frame replication and elimination, and you've got the capability to avoid congestion loss. That's basically your 3 things. If you nail down a path, then mobility becomes very difficult. So you still maybe need the other 2 components, but nailing down the path becomes very difficult because you have to update it all the time as the things move. And you don't even have time to do that and send the control to PC to say where you are. So if you really have a mobile application in mind, maybe Thomas will say something different, but in my view, you have to use a dynamic routing inside your thing, but maybe still program the flows at the edge so they can be delivered in due time. But then that means really having more buffer. It's closer to what 802.1 BA is doing, if I'm not wrong. So you mostly buffer at the edge.
Okay, thanks.
So Thomas Otena, I can try answering your question. There are tens of thousands of networks today, including wireless hard and IEC100, that use centralized scheduling, and it works fine. You're absolutely right that there's a limit to the mobility in those networks. And so that's why in 6TISCH we support both modes, centralized and distributed, but we don't answer the question how fast, how mobile is a network, and when do you have to switch from one to the other. I don't think it's within scope of the IETF to do this. It might be something, it's implementation specific or research wise, depending on how you want to define this.
question? Yes?
Just one quick question, Pascal. I think it's clear to me the time sensitivity is quite important for the, by the way, this is Chonggang. To the use case you list, like so industry control, vehicular, and smart grid. One question I have is, are you going to consider the scalability issue? Because for those use cases like a smart grid and vehicular you put there, we can imagine in the future there will be a great number of devices or nodes there. If we do this kind of centralized controller-based solution, the scalability could be an issue we can consider. For example, if we take this like SDN, like SDN approach, and then you probably need to consider the controller inter-controller interaction. Basically, you could say one controller probably has the limited capability for managing devices. Another thing is those devices from the use case listed there, they are quite diverse. If you consider one size fit all solution, probably there will be some issues. Some devices they are very powerful, others they have a constrained resource. So you may what's a protocol or what's a suitable protocol between the controller and the device? Are we going to use the PCIe or are we going to open flow? For example, open flow is based on TCP, or you are looking for some protocol based on UDP, something like that.
Yeah.
Just a question, you know. Yeah.
So the co-op draft is probably answering your question exactly. So we're using COMI as the constraint management interface to go and modify the schedules of the nodes. So the question about the protocol, the answer is in the co-op draft. This will be presented on Thursday. Yeah. So I encourage you to ask this question again on Thursday if you want. I apologize. Yes. I didn't mean co-op. Yeah. I mean the 6TISCH co-op draft.
Yeah, I just mentioned this scalability. A protocol overhead is one aspect, and the architecture could be another aspect. From the architecture design, you could consider this kind of scalability issue. Yeah.
Yes, we certainly, and I asked the very question to one of the authors of the smart grid thing is, what's the scale of your network? Do I need to coordinate between PCs to design those flows? So it's an open question I have to actually the authors. And that's an interesting question. It's really a very good question.
Thank you. So we're back on our usual schedule. And we have to move forward. We're right on time. René, is it okay if you present now?
Oh, okay. Good afternoon. My name is René Struik. I would like to briefly go over the last 60 security draft that I posted early January. So let's see. Expression there at the point.
So I am the plan B. Plan B doesn't work either.
Okay. So I just want to briefly give an update on that document. As I put on this particular slide, the document actually has a slightly different title than the one I presented in Honolulu, which might have been confusing to some people. And essentially the difference between this document here, and I gave a little slideshow there as well, and this document is that it adds lots of detail, especially on the Mac functionality, since we are talking about 60s operating on the basis of 15.4e TSCH, and details on the joint protocol flows. And there's lots and lots of footnotes in all documents. It's about 18 pages. Nevertheless, there's still work to be done, so I will just go over what's there and what's still missing or what would be suitable next steps. So just to recap, the first few slides are just basically a recap of what was already discussed in Honolulu, just a refresher. So enrollment of the device is essentially.
You need to hold your mic here, but they can't hear you.
I'm not loud enough. Okay.
No, if you don't move it too much. Don't show with your mic.
I'm enthusiastic. Okay. Well, right? Okay. So enrollment contains three conceptual steps. So one of them is authentication. There's an authorization element, and then to get on the network and to get fully operational, you need a configuration stage. There are certain parameters or steps. So the layout is essentially like this. And this again, this is just kind of a boilerplate diagram. There's more detail in some later slides, and ultimately text is leading a figure. So we have three actors: joining the device that wants to get on the network. Then it talks with something that's now commonly called the joiner system, which is just the mechanism to reach through the network via a node that is already on the network. There's a last slide actually that discusses what happens if the neighbor node, if the joiner system is not on the network. And then it reaches out, and there's all kind of functionality somewhere residing on the network that allows, for example, IP address assignments, scheduling information to be pushed to the joining device, also authorization system to be taken. So this is the kind of the setting. So we have here these three stages again: authentication, authorization, configuration. They don't necessarily have to happen in one particular order, but obviously if you do design, then you will have some partial ordering because of technical requirements. Then also already put forward, I think in Honolulu, what are the desired properties? In a nutshell, you would, of course, you want the protocol to be secure because you don't want to have unauthorized access to the network. Ideally, I think privacy would also be an interesting feature, and especially in our setting in 6TISCH, we really want to make sure that we take care of minimizing communication time latency. And since we're talking about constrained devices, we want to move essentially the resource utilization to the devices that can afford it. And then some general things like, I think it's good to stick to separation of concerns if you can, minimize dependencies, just lots of these things have to do with general design. And flexibility so that we can create different deployments. So this was also discussed in Honolulu. Okay. The guy in the middle is going to disappear, I guess, right? Okay. So essentially the protocol has more or less the following structure. A joining node, it listens to a beacon. Based on what it hears, it may decide to initiate the join protocol. It exchanges a message with this neighbor router, this join system, after which it can, sets up the communication with basically the mothership, the server that may be multiple hops away. And during this process, a key is established in this particular setting. So this is a security-centric view of the world. First with the neighbor node, the joiner system, and then this the server node, which is in the document, the draft is called the. And once everything is okay, and authentication, authorization is satisfied, configuration data is exchanged between the joining node and the JCE, and scheduling information can be pushed. And then in Honolulu, I also discussed optimization. This is on the next slide. Yes? And you see here that if you look at the differences, these are four communications that may be multiple hop, and every hop costs a couple of seconds. So we like to minimize that. And if we can apply a magic of caching, then we can reduce it to the minimum possible. So if you ever have to, during this whole process, have to reach out to a server node, then you would have to do at least one communication to that server and one communication back. So that So in Honolulu, the status was, and then you realize all these properties that are on the slide. So in Honolulu, the status was we didn't really have the details in the draft. Okay. Before I go there, so this is the high level picture of the joining process. Here we have these guys who want to get on the network. It does some local communication with something basically on the border of the network, and then it does one communication with the center. So what's the current draft? The current draft actually does away with the hand waving and provides lots of detail. So there's lots of detail on MAC behavior, triggered by some cross-reference to the 4 specification. And there's lots of detail on the joint protocol itself, at least the proposal for it, including protocol flows and design considerations. So that's why it's not like 4 pages. And the protocol flows also take into account this caching, so that you reduce the non-local communication flows. What did we assume in the draft? The draft assumed that we could design ideal design focusing on security first, so to speak. And the assumption is, in the description at least, is that we have devices that have a public key functionality on board and are able to verify each other's certificate. So it's a certificate basically in the draft. This being said, most of the flows and even most of the description, because we didn't really bite and frame structure elements yet, most of the structure really fits also even non-publicly based approaches. So I think it's extensible. It's not currently there, but I just wanted to note that this is not just for certificate only applications. And what did we assume on the routing functionality? The only thing we assumed is that there is a communication path between the join assistant and the server. We don't necessarily assume it's secure. Obviously, we don't necessarily assume that the join assistant is part of the TSCH network. If it's not, then you never have a network key that you can share with it. So there's somewhere in the footnotes, there's about 5 footnotes about this particular property. And that's to accommodate also people who look at our deployment models. And I think there's people who are on this list also probably on the 6th low list, and there's lots of bootstrapping related drafts around. So I just want to make sure that some of the footnotes accommodate the fears of people that this would only fit this TSCH. But definitely it's triggered by TSCH desired behavior. So this is the current draft. Then what still needs to be done? A lot, because lots of details have to be filled out. So that's all the mostly blue stuff here. I think we need to look at a scenario where devices don't have the initial setup requirement that I assumed for the joint protocol. So I assumed that devices have a cert on board and that they can they can verify each other's certificate. What happens if that's not the case? Then you need to basically get this thing again, right? So we need to basically have something that can synchronize behavior between the joining node and something in the network. And I think I already mentioned that I think the general philosophy also mentions non-publicly based approaches. So I think we could extend it also in that direction, if that's what people want. And there may be some security details that will change them, but in principle, I think it's possible. Then on the joint protocol, there are no packets yet in the draft. It's all about flows and what to do. It's basically more on a cryptographic level than on byte number 7 has this in the structure level. So obviously that has to happen, and we have to take some picks there on what kind of formats are we going to use, what kind of specifications, and so on. So right now it's more conceptual than that. Then on the security front, right now the design is really triggered by maximum security that you can get away with, trying to prevent denial of service attacks. But maybe there are some scenarios where people think, at least, that denial of service attacks will never happen. So I think that's why I have the word study here. What's the impact if you relax those security conditions? Maybe then there's slightly less of an overhead on this joining systems before it passes information to the server. The second one is, okay, what happens if we don't use public key-based techniques? Then I think I'm a big fan of looking at these designs from a system perspective. So I think we really have to look at not just protocol number n+1 that does key agreement. We also have to say, how do we get keys into devices? What is the deployment lifecycle? Because in the end, we won't have a system that works. Then I already have actually some text on most of these areas. But
I'm sorry, can I just, about this initial and deployment lifecycle, there is a working group called SACM, and they are looking at actually the device lifecycle. So when the posture of the device, I mean, what kind of credentials it owns, which kinds of variation of a protocol it runs, if there is a flow found in the protocol, it needs to be updated, something like that. So they're looking at the whole life cycle. So it could be good to have a pointer on that work and see how this relates.
Yeah, so I don't really know exactly what current status of some of these things is, but definitely we should look at taking advantage of that. So then I think we also have to add some text on the privacy considerations. I think since about 1.5 years, I think it should not be just the security considerations section, it's also the privacy considerations section in every draft. And I think if I look at it as, like Internet of Things, global 50 billion device aspirations, I think it's crucial. And then I think we also need to have more detail on what happens if, for example, one device gets compromised. Does it sync the whole ship, or does it sync only one device? Then on the routing model, currently the draft assumes connectivity between the joint systems and server, DCE. There needs to be detail on all kind of routing favorites, like IP address assignment, or how do we get it, something on network discovery, and ideally it doesn't blow up the number of messages exchanged by a lot. Because lots of people have been complaining like security always adds lots of overhead, but I've been looking at some of these network discovery drafts, and they terrify me. So maybe we can do something here, especially because TFCH is also right now, the schedule is being triggered by basically one mothership. So maybe we can do something smart there. So this is, I have here final notes, but I also have 2 pictures after that. Okay? So we have lots of drafts in all the different groups, and I think actually I would like to see less drafts and more unity. So let's try to get there. And let's try to accommodate also all these different use cases. Random provisioning order, sequential provisioning order, let's try to make everybody happy. I think it's possible. And I think security policy profiling would help a lot there. This is the vision I have for the final draft, if it will ever happen. So we will not have just a join scenario where we have one server. We will have a way to distribute some of this functionality. So basically, it's UFO with like 3 of these things again. And then we will also have this scenario. Oh yeah, it does allow me. So this is the kind of, which I think is kind of a fun scenario. So suppose you do provision a network, you just have a bag of devices you don't care about. You sprinkle them all, and those are the red guys. They're not even secured necessarily, but they help you in communicating messages back and forth and initially provisioning the network. And after that, he does basically vacuum them all up, and then all the remaining non-red devices are your network. So maybe that's if we can facilitate some of these scenarios, maybe we can even get our total time latency of setting up a network is 1,000 nodes down. It's kind of a little bit inspired by some discussions with some of the building control people. I don't know if they have the same vision, but I thought it was kind of cool idea that basically it is disposable devices that configuration crews can just sprinkle along and without any security concerns. I hope that it can all end up in the final draft, but some of these concepts. But let's first do the one without all these transitions. Okay.
Thanks a lot, René. Questions? And please keep in mind that we are presenting all this today in the context of rechartering. So.
Hi, Sandeep here. I think it's great that you're also looking at other PSK-based models also, apart from certificates also. One question is, hello. Do you also consider that the device, so you looked at the device authorized to join network, but does the device care that should it join this network?
So in the draft there's some language right now that it could decide that's an authorization question, right? So the device could decide not to become part of the network or not, based on obviously it should basically based partly on authentication considerations, so that's where the chapter comes in, but also authorization policies. And some of these policies could come from network like the DHCP, but it could also be a local system criteria. Right?
But that's only a one-way authorization, right? It's not two ways. The network deciding you can join network, but the device cannot decide that should I join.
The device, of course, has to have a criterion to judge that, right? And either the criterion is available on the device itself, or it's used to the device by some kind of authority to do that, or it includes even include the human device interaction by pushing a button for another.
Do you have it in the requirements, or do you have it in the requirements, or is it?
It's not in the requirements in that much detail, because then you get into the whole authorization life cycle, and there's lots of things to security, but this is just trying to focus mostly on the joint protocol. So, for example, there's also no language on how many CAs can there be, and so on. Like lots of these things are more policy related, no matter how important they are. Right? But ultimately, like if it was 10 years down the road and none of these things have been addressed, then everything is fixed, right? So, yeah.
Any further questions?
Can I ask a question to the group? Like,
please.
For those who have read the draft, do you think that it is extensible in a way that actually could work? Because sometimes security discussions get all heated and nobody seems to agree and so on. But so personally, I think it could work, and it's if we fill in some blanks. But I would obviously I can always agree with myself, but we have lots of smart people in the room, so. Any comments?
So I have read your draft in great detail, and I like your presentation. It's very, very general, and I think it's a good base to build upon. One of the general comments, but that you highlighted in your slide a couple of slides ago, is the need to support PSK, as you highlighted, and I think we should make sure that both modes are in there, because from the analysis that we've done in the security design team, using a full-fledged security certificate-based solution might take a lot of time or might take a lot of bandwidth, and so we should be able to switch between one mode to the other. Wireless HART, for example, uses something that looks like PSK. So I'd like to to make sure that we have both modes. But from your presentation, it looks like, and from your blue bullet a couple of slides ago, it looks like there's space for this.
Yeah. So I think there's certainly space for it. I think we need also a little bit more detail, like what do you buy for it, and what are the trade-offs, right? So I'm not saying that we should not do it. So don't get me wrong.
Yeah.
But I think the conclusion of what is the benefits requirement, I think it's a little bit premature right now. But
yeah. I mean,
I think we definitely need to work on that direction because we need to have all the data points.
Yeah.
To do all the right trade-offs.
Yeah, it's really to authenticate, to show the PCE or the JCE that the node that is joining is in fact who is, and so if you have a shared secret between both, that's a kind of a.
But this ties into the. I think we need to work out all these scenarios.
Yeah.
Fit them in there, but this will be particularly an interesting point, where we have to look how it all fits, because some scenarios easily fit with what I usually call a homogeneous deployment scenario, and others with a heterogeneous one. And there's some detail that a few slides ago I put in denial of service. There are slightly different properties, but I think we can definitely we should consider all these cases.
Okay.
I agree that.
Okay. It should work.
Robert Grady. So, with regards to the plethora of drafts and things like that, how do you think we should attempt to try and unify? I mean, so the first question is, because there are so many different drafts going on in lots of different groups, does that suggest that it's going to be difficult to do and there's a reason for having all these different drafts, or do you really think there's a way of unifying it all?
Well, I certainly hope that if the enrollment people find enough drafts, that they all actively contribute to the discussion. Because I think that's it's good to produce drafts, but there should be more discussion also on working out some of the details.
So for example, you put there, you need to define what the joint protocol is. So that's going to be very specific to 6TISCH, and therefore you're going to keep going on with this focused solution for a particular architecture and so on.
I think there are certain aspects that depend on Mac functionality right now. If you look at the current draft, you cannot completely deploy it from TSCH, but I think 95% of it is independent.
And that's a good point, because I think the way you've written the draft is very good, because it does generalize the concept set. I think you could take some of the structure of what you're doing there and make it more general and apply it to the number of groups.
And the main sections are basically neck behavior. Right now, the section is not in there, but the neck behavior is really spelled out over a bunch of pages. And then the joint protocol, it does cross-reference the neck somewhere. But if you look at all the, apart from the 50 security notes, it doesn't really. It's not like 15.4 here, 15.4 there, right?
Okay, just one before Subir. We have formed an IoT directorate at the IETF, and there is also a meeting that was organized by James Woodyatt on probably Thursday, which will be more specific about all those drafts on security here and there. And so there will be certainly an effort over the next period of time to consolidate the work, put people together, and I think that the IoT Directorate will have a role to play to make sure this happens. So this is going on, this has started.
The only thing I hope that is not going to happen is that, all different groups are doing something. Let's start a UN of bootstrapping protocols, and then in 2028 we're going to meet again. I think we can move forward with some things. Right?
So I think I agree, Pascal. I think that's within IETF, having a general architecture which can be applicable, and then different maps, maybe they're different bucket format, but when we are using all 15.4, right, we should have one approach and to do that. I think that would be good for the community, right? Then I have a specific question to the chairs. I think you mentioned that there will be charter discussions on that, right?
Right now.
So after that, there will be security also included?
Yeah. If you leave room to it, but yes, we'll force you to do that.
This is Samita again with Sixth Law Co-Chair Nathan. If you think that you are going to generalize this solution and make it applicable to other groups, especially Sixth Law, there are two technologies, I would encourage to also get some time slots, not this time, but maybe later, to discuss it jointly with the Sixth Law group. And of course, we can start discussion in the middle list. And also for the six-ish group in this room, we would like to mention that we are jointly arranging meetup on Thursday evening. More information will be sent out for security-related discussion on the constraint node networks, especially looking into bootstrapping and other related work.
So the date, just clarifying question, it's Thursdays,
5 p.m.
at 7 p.m., right? Yeah. So it's final now? It's tentative or it's final?
Yeah, so the poll suggests that most of the people.
Poll suggests, yeah. Okay. So that
We need to still find a location and where to meet.
Okay.
So basically 7 p.m. I would say James Woodard is arranging this. He's the secretary.
So yeah. So one comment about that date is that it's after the 6-ish meeting from Thursday morning. So
It's an informal meeting.
it is. But if it's absolutely an informal meeting, but since we're going to talk about rechartering, anyways, since it's informal, it doesn't matter. But it would have been good to have it before.
There are still very close options in the doodle, but the best was Thursday. Okay, thanks, Amita. We really need to move on. Okay.
Everybody for Sixth Law, please read the draft comments, grab me in the hallway, keep me up if you want.
Thank you, René. Thank you very much.
So we've got 15 minutes left, and the goal of those 15 minutes is to start the rechartering discussion based on the two items that we've discussed today. So one of those items is deterministic networking and centralized scheduling for 6-ish. Basically, mirroring what's being done by several other OSR, and then the security discussion. And for both topics, the question to the group is, what are we ready, what are we capable of taking inside this group, and else, what could happen somewhere else. So for DevNet, what we have, I think, is very mature requirements, because we mostly inherit them from ISA 100 and OSR. So we know exactly what we want. We actually could take additional inspiration from the dev network, in particular for this frame replication and elimination thing, which is really a great way to augment the delivery ratio within schedule. We have a very elaborate DevNet architecture. It's already a very complete document. I urge people who are interested in centralized scheduling for 6-ish to read this document. And the question to the group would be then, what within this architecture applies to 6-ish and what does not? By reading it, is mostly completely applies to the orders of magnitude change between Ethernet, which is great concern for some of this activity, and 6-ish. So what we try today is incubation. We try to present DevNet, but certainly that cannot happen deeply because that's not our charter. So the first question to the group is, should we speed up some work? Can we take just a 6-ish view of DevNet and try to work it out within 6-ish? Or should we help fork a DevNet working group that would basically take away the burden for us and deal with CKL, deal with PC, deal with T's, and all the others. And then we would only deal with DetNet. See? So anyone, any idea on this?
I think, Pascal.
Subir.
Subir does. Sorry. Your last approach, right? Because I think that if you are really rechartering, and you want to include everything for the DetNet, I don't know whether, even extending the 60s can accommodate all the things, right? So maybe that, little bit incubation and then create a new, a separate one which can take care of the remaining of the centralized scheduling and all these things there, because my sense without, physically seeing everything, that even if we extend it, maybe that, again you have to recharter to accommodate other things, because I've seen some of the use cases and also hearing that other need for the, industrial automation. Maybe that a separate group with a more elaborate charter would be better. That's my view.
Pat Kenning, Kentucky. I agree with Subir. I think that a DetNet work group would facilitate a good system understanding and would help us, I think, in the long run. I understand the first trying to work DetNet as only from a 6-TISCH point of view, but I think in the long term we'd be better off by participating in a DetNet work group.
Thanks, Pat. So what I need to point out here is we've got Chonggang's draft about, currently it's a use case draft, how TSCH, deterministic TSCH can be used practically in process control applications. Chonggang, what I really would love your draft to become is something closer to the requirements draft that we have for DetNet, which really spell out things like, I've got so many devices on my network. I have so many tracks across my network. The kind of end-to-end latency that we expect is this. The kind of loss ratio that we expect is this. And with those numbers, then we can really come to DetNet and say, can I use your architecture? Can I use your model? Can I use your flows and your descriptors and your data models so as to actually push my topology into your controller, have the PC compute all those tracks, and feed that back into 6-TISCH with the same homogeneous architecture as DetNet has.
So the microphone doesn't work.
Aside from, this one seems to work.
That's why it works, yeah.
Aside from obvious things about whether you're thinking primarily about wired networks or whether you're thinking primarily about wireless networks, DetNet has a number of use cases, a number of constituencies. I was last week at Meyer Sound Labs, where I saw tremendous demonstrations of extremely high-speed audio and video being, we're talking multi-HD, multiple times HD streams on 10 gigabit fibers that need the DetNet so that they can go through routers as well as bridges. There's a lot of things going on that are not necessarily the primary focus of 6-TISCH. And so I would really, after we had our first a side meeting, we don't call them barb-offs, I'm told, anymore, in Ottawa. And I really think it's time to get this moving or forget about it. So I'd really like to see a BOF for DetNet in Prague, because it's time to get it moving or quit wasting people's time. And I think we can get it moving because we have a lot of stuff going.
So I think it's a recommendation from the working group that, one, we don't try to take all the DetNet-related work inside 6-TISCH. Second, we should document our requirements more tightly in the practically same shape and form as for instance the draft about the boundary. And third, we should help for our own interest the formation of this network. So the second item was security. Same question with Martina?
No. Done.
No?
But we have a second session on Thursday. So we asked for two sessions, a long one and a short one. The short one was for things which are outside, and we got the short session first. So it's kind of weird that we started with not truly 6-TISCH pure central things. But the big session is on Thursday, and we'll finish by a large part on rechartering. And so I propose that the discussion about security, we have it at that point. Is that okay with you? So Thursday morning, 9 to 11:30, this same room, and we'll go through the chartered items, the work group docs, and then finish by rechartering. Thank you very much.
Don't miss it. Don't miss it. Don't miss it.
I'm sorry? Yes. Did everybody sign the... So with this, we conclude the session. Thank you very much. Did everybody sign the blue sheets? Yes, you have them there. Anybody missing? Thank you.
So we have troubles with some mics.
Want to start? Yeah, of course.
So that's zeros now.